Hi, I'm Lawrence Krauss, and welcome to the Origins podcast. This episode is with the geophysicist Dorian Abbot. Dorian is a young and upcoming associate professor at the University of Chicago whose research involves mathematical modeling of climate, complex issues like cloud feedback and other things, and that leads him to try not just to understand climate today, but also the paleoclimate of the Earth, the ancient history of the Earth, and how climate has changed. And of course, that's led his research not just to thinking about climate here on Earth, but equally interesting, or for some people more interesting, the possible climates on exoplanets. Because if we ever want to understand habitable planets, which planets might be habitable, we need to understand how climate might occur and respond in environments that are very different than those on Earth. And Dorian has done a lot of work in those areas. And we talked a lot about climate and the early history of life and the evolution of our climate here on Earth, and also possibility of life elsewhere in the universe. But Dorian also became of public interest recently. He was asked to give a public lecture at MIT on climate and exoplanets, and that lecture was canceled as a result of an op-ed he'd written earlier in Newsweek magazine criticizing current diversity, equity, inclusion practices at universities, which he argued worked against merit. And that created a furor. That cancellation created a furor, not just at MIT, but throughout the academic community and among the public. And Dorian later gave his lecture through an organization at MIT, an online lecture. So we talked about that issue at universities and his concern and mine about what's going on in terms of free speech and attacks on merit. And so the conversation was twofold, both on the detailed science of planetary environments and also on what's happening at universities today. So I hope you'll enjoy it. I certainly enjoyed the discussion with Dorian. And whether you watch this on our YouTube channel, where I hope you'll subscribe if you watch it there, and so you can hear more about our podcasts, or whether you want to see the ad-free version on our Critical Mass, my Critical Mass Substack site, where you can now see ad-free videos of all the podcasts, as well as all of the audio versions as well. I hope you'll consider, if you do that, getting a subscription to Critical Mass, lawrencekrauss.substack.com. That supports the podcast and the Origins Project Foundation that produces the podcast, our nonprofit foundation. So either way, no matter how you listen or watch the podcast, I hope you enjoy it. Thanks. Well, thank you very much, Dorian, for agreeing to be on the podcast. It's great to be with you virtually.
Great, good to be here.
There's a lot I want to talk to you about, and but I want to. This is an Origins podcast, and I want to begin with your origins, which I've been studying. And you did all your degrees at Harvard, right? You must have liked it there.
Yeah, I enjoyed it there. I studied physics. It was fun as an undergrad, and then actually Howard Georgi. Have you ever heard of him?
Of Howard, yes, I was at Harvard in the physics department, and Howard is a old friend. Yeah.
Yeah, and he taught the physics intro class. Can't remember what it was called, but there was a special advanced physics class that was super fun.
I remember. Yeah, he had me teach it one day once. Yeah, it was sort of physics for hotshots, I think, or something like that.
Yeah, that was fun, and then I ended up sort of transitioning more into applied math, but I kept the physics major. But there was someone named Howard Stone in the applied math department or like engineering department, and I really liked his fluids classes and his differential equations classes. So I got more interested in that stuff, and then I did my PhD in applied math, and I worked on earth science problems.
Yeah, I noticed that. Well, we'll get there. I mean, I was wondering about the transition from physics to math, but I actually jumped ahead of where I'd really planned to go, which is well before Harvard. You obviously did well in school because you got there, but what got you interested in science? What are your parents? Are they academics? Or are they?
No, my dad was a carpenter and a school teacher, and my mother was a social worker. They're both retired now, and they were not really interested in science. But my mother's father is an inventor and an engineer, and he's still inventing. He's 90 now.
Oh, great.
And my uncle, his son, is an engineer. And so I grew up in Maine, and we would go out, they would take me out in boats a lot. And I learned a lot about waves and weather and things like that. And so that's sort of what got me interested in talking to them.
Okay, what did your father teach, by the way? What did he teach in school?
Middle school English and history.
History. So they were that other side of the brain kind of thing. But
Yeah,
um,
I think they never really took math past 8th grade. In fact, it's actually interesting. After my dad retired, he started at a community college. He started taking more math classes.
oh,
He's sort of
neat.
gotten bored with that now, but it was actually pretty fun. He got all the way up to pre-calculus,
Did,
and it was fun to talk to him about it.
did you help him? Did he ask for your help?
Yeah. He would call me up, and I would show him how to do stuff.
Oh, that's great. Oh, that's fantastic. Well, so but it was an uncle then, and that got you interested in what, waves and weather. So you decide to go to Harvard, still on the East Coast, and as I say, did physics. And Howard, Georgia didn't manage to convince you to do particle physics, I guess. Um,
No.
it was a
Well,
stronger
so I
path.
made an evaluation after that intro class that with all these advanced students, that there were too many smart people chasing after too few prizes. And so I started sniffing around for other areas.
That's-
And actually, I had read that the Gleich book, Chaos, as a
yeah,
high school student, and I was really interested in that. And a guy named Daniel Fisher taught a
I know,
class
I know Dan Fisher. Sure, yeah.
on nonlinear dynamics using the Strogatz book that I
Mm.
took as a sophomore, I think, and I really loved that class. And so then I remembered I had read in Gleich's book, he went into Lorenz and stuff, and so that's where it kind of clicked for me. Maybe I should sniff around that area, atmospheric science, climate, to
Well,
find
it's
fun.
certainly, yeah, it's certainly an area with a lot more problems to solve. I think you made a wise choice. I know I often hear that happens, especially at a place like Harvard, where there are lots of sort of good students jockeying to get into to things like particle physics or whatever, or string theory, um, and fluids and clearly you're interested in fluids, which your PhD was on sort of fluids in a way as well, right? And
Yeah,
um,
fluids and numerical methods.
and that and did you so was your interest I mean, it was applied math, but was your interest applied in the sense of thinking about things like climate, or was it just the fascination about the understanding fluid dynamics and potential chaos and that sort of thing?
I would say both. It was in both directions. It was the heavily applied side of applied math. So the applied math department at Harvard has a reputation of almost being a physics department. And I think that was true. Like, I didn't do any proofs or anything like that.
Well, I noticed that applied math is in the engineering school. Is that right?
Yeah.
Did you get a degree? Did you get officially an engineering degree or no?
Technically it's, yeah, the school, the CEAS, the School of Engineering and Applied Science.
Okay, so
So
that,
yeah, I
but
guess so.
yeah, so that, but your undergraduate was in arts and sciences because you were primarily a physics major, but your PhD was in,
Exactly. Yeah.
okay, and then you were interested in probably what I think is apparently one of the big problems, and still is a big problem when it comes to terrestrial climate change, which is cloud feedback on climate.
Yeah,
And
exactly. Yeah.
let's talk about that a little bit, because I've written a book on the physics of climate change as
Yeah.
as an outsider, and the motivation for that being that if I, as a non-climate scientist, couldn't understand and explain climate science, then there wasn't much hope for public
Mhm.
discussion in that regard. So I thought that was part of the reason for doing it. But you're an expert. But one of the I get a lot of feedback, and obviously I talked to a lot of colleagues, some of whom may have taught you, or been your colleagues. But obviously people say, well, what about clouds? And that's always the big, well, that's often a big issue. So what
Yeah.
about clouds?
Well, so first of all, why are they hard to model? We have various ways we can attack the climate problem. One is empirically. You can look at past climates, look at their temperatures, but you've got to try to infer their temperatures,
Yeah.
and look at their CO2. If you can try to infer what the CO2 was, and then you can say, okay, if the temperature is this, then if the CO2 is this, the temperature is this, and that's what the climate sensitivity should be, which is, like the if you double CO2, how much temperature changes. There's all sorts of uncertainties in that, because it's hard to infer the CO2. It's hard to infer the temperature in the past. And there could be other things forcing the climate other than CO2, like the methane could have changed and you would have no idea. So that's one way you can get at this. Another way is just sort of like basic physics. So you can sort of reason your way from basic physics. And when you do that, actually Arrhenius did this in 1896. You get, a reasonable estimate of the climate sensitivity, but with a large uncertainty because there's other processes like clouds.
Yeah, but one thing about, I have quote Arrhenius in my book, by the way, and it looked at I have his data in the book. And it is amazing how close he got, especially since he really didn't have, this whole field depends on data, and the data he was working from was he made wild extrapolations based on the data he had. It was kind of amazing.
Yeah, it was moonshine, right?
Yeah.
Not the liquor, but earthshine coming off the moon.
You got it. That's right. Yeah. Glad you explained that for the audience.
So, okay, so then you can try to build a global climate model to try to do this, and that's another method you can take. And when you do that, because of our computational limitations, your grid resolution is about the size of a large city like Chicago. It's like order of 100 kilometers by order of 100 kilometers. It gets a little smaller, but it's not an order of magnitude smaller. And so the problem is clouds exist on smaller scales than that. So the things that you resolve at the grid level, temperature, humidity, winds, that's too large a scale compared to clouds. So you have to try to extrapolate down to a smaller scale, and there's a huge amount of uncertainty in doing that. We call it, a subgrid scale process in any model is going to be uncertain. And so what you do is you try to come up with some theoretically motivated empirical parameterization, and you fit it to the available data, but then we don't know if it's going to work in the future. Yeah. And so that's the main reason that the different models give different results when we go into the future, because of this uncertainty. And so it's the main thing that, at least for this century, the last 20 years, people have been trying to attack and narrow down that uncertainty and understand clouds better.
Now, the IPCC, of course, includes clouds along with their uncertainty when they're considering radiative forcing, and which is basically the one physical number that says how much additional heat is being stored in the Earth compared to the amount that's being radiated out to space. And they put some uncertainties in that. How do they are in your opinion? I don't know if you impact with the IPCC if you're on that, but how does one estimate the uncertainties? By trying different models and seeing what happens, or by doing paleoclimate, or what?
Well, okay, so there's the radiative forcing, but then there's the feedback, and the clouds have a little bit of influence on the radiative forcing, but they have much more influence on the feedback. And
you want to explain the feedback mechanism
So for cloud, okay, so let's start with a simple feedback mechanism, which would be the ice albedo feedback. So when you warm the planet up, you get less ice. That means the planet reflects less sunlight, so it keeps warming. So that's a positive feedback. Now with clouds, it's actually gets really tricky, because clouds can both trap Earth's radiation going out to space and warm the planet more, but they can also reflect the sun's light and cool the planet. So they have both effects.
Yeah.
And either one could change in a positive or negative way. And so you have these sort of four ways that the cloud feedback could be positive or negative. So just to give you a simple example, suppose you have these thick stratus cloud decks off near the equator off the coast of South America. If those things reflect a lot of sunlight, and they're at the equator, so they get a lot of sunlight. And if you get less of those in the future, then you would absorb more sunlight, have a positive feedback. But if you get more of those, you'd absorb less sunlight and have a negative feedback. And unfortunately, we don't really have the capability to say for certain which way that sort of a feedback will go.
Yeah, no, it's interesting. I mean, even on a much larger grid scale than clouds, that one of the problems is there are many effects of climate change, and people focus on temperature, but there's also moisture. And it's quite differential. There'll be parts of the Earth that'll become much drier. There'll become parts of the Earth that'll be much warmer, and part of that depends on also fluid flow, namely the oceans, and obviously the cloud situation in the equator will depend on the increase in moisture there with heat, etc. And I forget now, in fact, I have in my book, but I forget whether the prediction is that the moisture will increase. I know in sub-Saharan Africa, parts of it will get much less rain than it has now, along with some of the American Southwest. But I forget what the predictions in the middle, in the equatorial
here's
region.
the typical, like the the theory level naive prediction. So
Okay.
the relative humidity seems to stay roughly constant, which tells you the fraction of saturation that the air is.
Yeah.
And so there's some theoretical justifications for that, but they're not that important. Basically, the relative humidity stays roughly constant, which means that as temperature, the absolute humidity goes up a lot.
Okay.
The total amount of precipitation and evaporation is mostly constrained by sunlight absorbed. It's an energetic constraint. So that's what, to zeroth order, the Earth absorbs sunlight and evaporates water, especially in the tropics. So that's the energy exchange at the surface. And so you're not really changing with global warming the amount of sunlight absorbed. You get about the same total amount of evaporation and precipitation. However, because the air has more moisture, specific humidity, more actual moisture in terms of grams per kilogram of air, for the same air current, you can move more water around. And the reason you have relatively dry and relatively wet places is that you move the moisture from the dry places to the wet. And so the sort of naive prediction is that the wet places will get wetter and the dry will get drier. Now, it's a little confusing because, you can have other effects like monsoons and stuff that can change, but that's what you were referring to with why, people often say the Sahara will get drier.
Yeah.
Like
It's a cloud. As far as I can see, that clouds are one big area of uncertainty, and obviously ocean currents, which is another area of your interest, I guess, in the sense of fluid flow, are going to be a dramatic impact on at least the differential impact of climate change around the world, and that's a pretty complicated area. Let's talk about clouds, and then I want to see if you have anything to say on fluids. But so if the equatorial regions become, say, cloudier, will the net effect be negative or positive, or is it still up in the air?
If the equatorial regions become cloudier, it will probably be a negative cloud feedback. So you'll get less warming than you would have thought. If they get less cloudy, it'll probably be a positive cloud feedback. But we should talk for a second about how you constrain the cloud feedback, like in the IPCC. Okay. So there's a couple ways to do that. One way would be so there's these subgrid scale parameterizations, and there's maybe like 10 parameters in there, which you can already feel that there's a lot of uncertainty there.
Yeah, with 10 parameters, you can, with 3 parameters or 4 parameters, you can fit an elephant or whatever that famous statement is. But anyway.
And then with 5, you can make his tail wiggle.
Yeah, that's right. Okay.
So you can go around to the experts who made those schemes, and you can say, what's the range for this parameter? What's the range for that parameter? And then you can do a Monte Carlo ensemble with all of those parameters perturbed. And what you do is then, so now you've got like 10,000 model runs, and then you use a keyhole, which is that it has to fit within some uncertainty the historical record. Like if it's totally bonkers, then we throw it out. And then afterwards, you look at what it does in the future, and that can give you an estimate of the uncertainty, at least within that single model. Then the other thing you can do is you can look at the different parameterizations across models. You see, the problem with the first method is you're using one physical parameterization. The problem with the second method is all of the models have similar histories, and often their schemes are originally citing the same papers. And so it could make you think that you have a better handle on the uncertainty than you actually do. Now, then you can also try to use historical evidence to infer what the cloud feedback was, based on taking into account feedbacks we think we understand better. And if we assume that all the extra uncertainty is in the clouds, then you can kind of estimate cloud feedback.
That's so the wiggle room is the clouds. Okay.
Yeah, that's typically how you'll approach it if you try to do this historically and empirically.
When you're talking, it reminded me of something that I read actually after I wrote my book, but since I've been lecturing on it, reading it, which is that an interesting fact, when one talks about uncertainty, I wrote a piece for a British magazine about the fact, sure, there's uncertainty, but that's what science is all about. It doesn't make it not science. It just means that we can quantify our uncertainties, which is one of the great strengths of science, not one of its weaknesses. But that a number of the IPCC models actually doing just what you said, which is going back and trying to fit the paleoclimate data, actually when they're estimating what the temperature rise will be in the future overestimate the temperature change in the past, and therefore they had to be constrained. Are you aware of any of that? Are you familiar with any of that?
Well, so I don't know specifically what you're referring to, but these models are tested in the past. And of course, there's the uncertainty that we don't know exactly what the CO2 was or what the temperature was. But we have proxies and they try to fit them. Matt Huber is someone at Purdue who's done a lot of that for the Eocene. And that's actually related to what my thesis was on. So my thesis was there's this period in the past called the Eocene where we have pretty good data about 50 million years ago. And we know that the planet was warmer, but it was especially warmer at the poles. So it was so warm at the poles that it never froze over during polar night. So you had crocodiles and palm trees in the Arctic Ocean. But at the equator, it was only a little bit warmer. And when you took a global climate model and increased the CO2, it got too warm at the equator in order to explain the poles. And so that was kind of like the tension. And we proposed a cloud feedback that could help be part of that explanation. And the way it sort of has gotten resolved over the past 15 years is the equatorial sea surface temperatures inched up a little bit, as they refined their methodology. And then it turned out that when you could increase the temperature even a little bit at the equator, you could get it much, much warmer because of feedbacks at the poles. There were a variety of feedbacks involved, and one of them seems to have been related to this cloud stuff we talked about. So it's kind of maybe a part of the story.
Okay, and so there was significant positive feedback at the poles due to less clouds, or
Yeah. So in this case, the specific thing we were talking about was at night so here's the real problem. How do you keep from freezing in the Arctic Ocean? So like you've turned off the sun for 6 months and you're radiating like mad away to space. So like, how do you keep from freezing over? And so we had kind of like a braking mechanism to help keep that from freezing over. And so the idea was not only are you radiating to space, but you also have a much warmer surface than the atmosphere because it's got this big bathtub of hot water, and that leads to convection and clouds, and that these clouds end up having a big blanket effect, radiative effect. So they trap the outgoing radiation and can help keep the Arctic from cooling quite as fast.
Sure, here up in where I now live up in Canada, you notice that on the nights when it's cloudy,
Exactly.
it's much warmer
Clear
than
day
the nights
versus
when it's
cloudy
not.
day.
Yeah, yeah. It's interesting. This feedback mechanism is interesting. Again, I learned about it recently in real terms, and when looking at the Greenland ice sheet and the likelihood that it might melt. Well, that it is melting, but and one of the things that I guess had at least that surprised people thought, okay, well, there'll be, the ocean temperatures will get warmer, and of course that's going to lead to some melting, but there'll be more snow. And the interesting thing in the two seasons that I know of, 2012, 2019, that had big melting, much more than normal, there was this effect where, in fact, there was a high pressure area got trapped over Greenland, and there were far fewer clouds. So not only were things warmer, but there was less incoming snow. And obviously,
double whammy.
Yeah, double whammy. And that, so those kind of things are obviously going to be important for detailed predictions. But let's go back. I just want to, so as someone who studied clouds, can we reliably say, as I often do, quoting at least my colleagues, that yes, there's uncertainty in cloud feedback, and yes, it's an important area of research, but it's not going to change, but it's not sufficient to invalidate the fact that there's net warming of the Earth?
Yes, I think that's 100% correct, what you just said. And so we know from the temperature records over the past 150 years that the global mean temperature has increased by about 2 degrees Celsius. And we know that the CO2 has increased by about 50%. And so we can measure this. It's 2 degrees Fahrenheit. I think I said Celsius. 2 degrees Fahrenheit, the correct number.
Yeah.
And so we know that Earth is warming. We know that it's because of the CO2. Nothing else has changed to explain that. This is sort of an argument about how bad it will be. It's not an argument about whether it's happening or not.
Yeah, I mean, the point is the clouds, the net effect, and there's some uncertainty, but it's not enough again, I think in terms of radiative forcing, because I guess that's how I learned this as I was thinking about it. But there's not enough to negate the increased radiative forcing due to carbon dioxide alone. And I was always amazed. And one of the things I tried to do in the book, if you're a physicist, it's amazing when a simple model comes up and gives, a reasonably good prediction. It tells you you're probably on the right track and that you can refine it. But it's really quite amazing how well you can do. Just a simple model, um, predicts, with a more or less linear relationship between. I mean, a multiplier, but with carbon dioxide abundance to temperature change, you can predict that the temperature of the Earth would have gone up by 1.2 degrees Celsius, and it has. And I often say if it walks like a duck and quacks like a duck, it's probably a duck. And it's really amazing how, and I think that's important for people to realize, especially since a lot of public effort talking about climate change as predictions of the future, that people don't realize that it's not all models, some of which have uncertainty, complex models. Of course, they're complex models, and of course, we're trying to make future predictions. But we have an incredible amount of data, and we can see we can measure what's actually happened, and the climate is changing, and we can measure it and compare it to theories. And correlation isn't causation, but if you have a good physical explanation and predicts more or less precisely what you see, it should give you great confidence.
Yeah, so that's the argument I try to make. So I have an article called "Conservation is Conservative." If your listeners search my name and "conservation is conservative," they can find it. It's my short article on. It's actually directed towards political conservatives.
That's great. Yeah,
about climate change. But at the beginning, I just summarized the basic evidence, and I think a lot of the arguing about our really uncertain data in the past, like the deep past, where we in the past 150 years we actually can measure the CO2 and the temperature, and we know what it was. The CO2 1960 we have literally measured it, and before that we have air bubbles in ice, so we know what it was. And in the future with the climate models, there certainly are uncertainties associated with them. But to me, what's convincing is just more than 100 years ago, the physics was worked out to make this prediction. People made the prediction. They say it's going to be a couple degrees if you double the CO2 about, and then that seems to be roughly what we're getting if we just measure and look at the CO2 change and measure the temperature change. And so, we're arguing, is it going to be 2 degrees? Is it going to be 4 degrees? But from a physics perspective, that's like down in the engineering details.
Well, if you're
correct.
If you're a cosmologist, order of magnitude is amazing, but like me, but it is. And, and that's the other thing you just mentioned that I kind of like to stress, and why spend so much time on the early history. This is well-defined physics. As I like to say, it's not rocket science. Rocket science isn't even rocket science, but it's well tested. It's the basic fundamental physics that you learn as an undergraduate, or some people in European countries as high school students. And it's the underlying science of radiation and is just, and absorption is just basic physics, and it's not in dispute at all. It's really fundamental science. And climate science is science in that regard, and so it's important. I'm glad you wrote an article for conservatives. One of the reasons in my book that I don't discuss policy at all is I think a lot of my experience from talking to people a lot is that conservatives, and to some extent libertarians, get turned off because they expect you to tell them, now we're going to tell you the government is going to make you do X. And the minute you tell them that, they don't want to hear any of the stuff before it. So if one can just talk about the underlying science and what's happening and say, okay, well, now you can make your own decisions about what you think needs to be done, but at least don't turn your ears off. Once you see this, then you can see it's a real issue, and then you can decide. Then it's a policy question, and then there are all sorts of political issues and political concerns, and people from the left and right can differ, but they can't differ on the science, or they shouldn't. As Moynihan once said, you can have your own opinions, but not your own facts.
Yeah. So in that article, I try to go through every type of person typically associated with the Republican Party and give an argument. So religious conservatives, traditional conservatives, business conservatives, and libertarians even. The libertarians were the toughest nut to crack. My argument was climate change should affect private property, and so you should care about it. But
There
the
you go.
traditional conservatives, I think, is the easiest nut to crack because it's a Burkean argument. It's
Sure.
the same thing as why you wouldn't want a revolution in your society, because the society has built up over many, many generations and you don't fully understand it. So you don't want to just do a revolution. And it's basically the same argument why you don't want to do climate change.
Well, that's a nice argument. Yeah, no. Well, as I said, the libertarian one I got mostly by saying, "Look, I'm not going to tell you what to do." So at least, at least you can. You know, I have a good friend who's a libertarian, and he was part of my audience when I was thinking about doing this. But we should also, as I've tried to stress more recently, it's really important to be balanced here. It's not just you know, quote unquote Republicans or conservatives. There's a lot. I get equally frustrated by overstatements on the left, which are equally bad. That the world is going to end in 12 years. That your children are going to die, because that gives fuel for people to not believe in this, and also to bury their heads in the sand. And so it's really important that both sides be based on science.
Well, so yeah, so it's an issue where nobody on either side is particularly well informed scientifically.
Yeah, yeah.
But
That's often the
each
case.
side is using it for their own political purposes. So what you just mentioned, the sort of extreme catastrophism is being used to try to push projects like the Green New Deal, that the people who are using talking about the catastrophe, they want that anyways.
Yeah,
so,
yeah. Yeah, no,
both sides.
yeah, it all gets filtered. A lot of it gets filtered, as you say, by what people want, and then they, you know, reason is the slave of passion, and it gets used that way. And I think it is, and you know, I think the fact that you say people aren't that well informed on either side, it's coming to people, some people like me, and now I think more you know, who do spend some of their time talking to the public to try and make make them informed enough so that they can, at least when they vote or take other actions, it's based on reality. Because even, you know, I've spoken out for years on issues like evolution, and it's often amazing that the people who kind of quote believe, although I had to use that word, I tell them I never use the word believe as a scientist, but who believe in evolution don't really,
yeah, they don't know the evidence.
they don't understand the basics of it, but they just, you know, they have a passionate reason for believing it as much as a scientific one. It's kind of interesting.
Yeah, well, I think in that case, the most important thing to do is for someone who has religious reasons for not believing in evolution is to point out the long religious tradition of interpreting sacred texts allegorically when appropriate. And the fact that the whole literal interpretation of Genesis is a very, very recent thing. It's a consequence of modernity, and hopefully that can.
Well, I mean, St. Augustine. There was, you know, you could look at all of these. Moses Maimonides. I mean, I've obviously spent a lot of time since I'm supposedly speak out for atheism, although it's not an issue that I'd rather speak out for science. But you know, Maimonides was the one who said something like, as he put it, the scriptures are absolutely true, but if your interpretation of the scriptures differs from the results of science, re-examine your interpretation of the scriptures. You know, and St. Augustine said that Bible isn't a scientific document. And anyway, well, okay. So look, I'm glad we were able to chat, and I learned a little bit already from you about climate change and cloud feedback, because it's really, I remember being in a public debate with a pal of mine who, this may take you to another area of your own research that I'm fascinated by. I first learned about and wrote about Snowball Earth when you were probably in middle school or something, and I learned about it from my friend Dan Schrag, who you may have interacted with at Harvard, and Dan and I were on a debate in Mexico about climate change, and an eminent scientists from MIT argued that we didn't understand clouds, and therefore climate change was nonsense.
Dick Linden, right?
Yeah, of course. Yeah.
The iris hypothesis.
Yeah. You want to talk?
To some people is known as the sphincter hypothesis because the iris is just one example of a sphincter muscle.
Yeah. Okay. Do you want to comment on his claim, because he gets a lot of press, you know, and I don't know whether you don't have to.
Dick Linden is an amazing scientist. He's you know, one of the founders of the field. Mm-hmm. His forte has always been critiquing, and this is a manifestation of that. He, I think, really helped the field a lot by pointing out things that other people were getting wrong. I mostly disagree. I mean, he doesn't say things that are ludicrously wrong. So, you know, I think he's arguing that the climate sensitivity is lower than other people think. He's not saying that that climate change is not going to happen. He's arguing that we're going to get less warming than other people think. And I think that's a possibility. Personally, my feeling is it's better to be safe than sorry. Since there's a lot of uncertainty in this, it's better not to underestimate his estimates are within the uncertainty, but I think he would put too high a confidence on his results.
On his own estimates. Yeah, sure. Exactly.
Yeah. And I think for me, there's also within that uncertainty, really bad scenarios. And so that's sort of how I would put it. But in general, Dick has been a huge inspiration for me. I took a class from him and it was amazing. And just the way that he thinks about problems really taught me a lot.
Yeah, it's interesting, and it's interesting, and also some concern because I've talked to him, and also my late friend Freeman Dyson, and my interpretation, and it's not maybe not fair because they're not here, is that Freeman is also a contrarian a lot, and they're both extremely smart people. Freeman was one of the smartest people I know or have ever known, and I think his feeling was he didn't trust the models because he wasn't doing them. And he figured he was smarter than the people who are doing the models. And I think that's a common trait among people who are very good. And it's good to be skeptical. But I think the problem is that when you assume, as someone once told Richard Feynman, actually, I don't know if he was alive when you were there, Sidney Coleman at Harvard, but he was a remarkable physicist. But he remember he once told Feynman that, you know, the other guys aren't all idiots, you know. You know, and so I think the idea is,
how did Feynman respond?
Oh, I think Feynman. Well, I didn't get his response, but I think his point was that Feynman. I wrote a book about Feynman. Feynman could have done a lot more if he had chosen to rely on other people instead of reinventing everything himself. But he wanted to do it to understand it, and I think you know, Feynman certainly didn't think everyone else was an idiot, but he certainly trusted his own intuition more than others, and you know and was often right about that. But your point that Lindzen's model or ideas are within the range of uncertainties that are already quoted, but he puts a much bigger prior on his results than other people's.
That's how I would describe it.
Yeah, I think that's important, and that may just be for the aficionados here, but it is relevant because it's worrisome when well-known scientists, it's important for them to speak out and be skeptical, but understate their own uncertainties and overstate others. And in my opinion, I guess that's the concern of some sense. But anyway, I was heading to Schrag because you also did some work. I noticed one of your papers on Snowball Earth, a recent paper, I think, of yours on Snowball Earth, and that will lead me to looking at the other area we've been spending a lot of time on, which is exoplanets and habitability. So talk to me about your work on Snowball Earth.
Well, okay. So I gave a talk once at Max Planck Institute around the period I started working on Snowball Earth. And someone came up to me afterwards, a German guy, and he told me like, some former director of Max Planck Institute told me this, and I'm going to tell it to you. The story was the first guy gets the order of magnitude, the second guy gets within a factor of 2, and then we leave it to the engineers. And that's how science is supposed to work. And he said, I like you because you go searching for the order of magnitude questions. And that's how I got on Snowball Earth, because there's just so much stuff that we don't have any idea what's going on with the Snowball Earth. So that's why it's fun. So I'll just say what it is. So It seems that there's 2 time periods around 600 to 800 million years ago, and around 2.2 to 2.4 billion years ago, where the ocean was either completely covered in ice, not frozen to the bottom, but the surface was covered in ice, or very nearly so, and where on the equator, the continents had ice sheets like on Antarctica, but they were at the equator and they were flowing into the ocean. So those are the basic piece of evidence. And we know that because we have the ability to date rocks, and because geologists can look at rocks and figure out if there were glaciers there, and you know, they have these scratches on them that they call striations, and then they have like rocks that get dragged out and dropped into mud that can only happen from glaciers.
And also, I think from magnetic field, from
Yeah.
iron, you can see where they are in the
Yes.
magnetic field of the Earth.
Right. So that's how you can tell there was ice. And then you can look at the magnetic field. There are certain types of rocks that lock in the magnetic field. And if it's mostly horizontal, you must have been near the equator. And if it's mostly vertical, you must have been near the pole. And you get enough of these different types of evidence on different continents and stuff, and you can put together the story that the entire planet had these ice sheets at the equator. And then with various geochemical evidences, you can start to argue about whether the whole ocean was covered in ice or almost the whole ocean, things like that. And so those are sort of fun. It's a fun problem because we know almost nothing about it. And then the other interesting thing about that is if you know anything about Earth history, you know that those two time periods were really critical time periods. So both of those two time periods I mentioned are associated with large increases in oxygen and changes in life.
Yeah.
So particularly the last one, animal life takes off after that last snowball era. And so it's not clear what the causal direction is, but there's something interesting about the changes in the atmospheric composition and increases in the complexity of life that seems to be related to the snowball periods.
Yeah, no, for me, it's fascinating as an older person now that to see the change. When I first heard about this, it was probably in the 90s from Dan Schrag, and I remember it impacted on me because I wrote a book called Atom, which is a biography of an individual atom, an oxygen atom, from the beginning of the universe to the end.
Wow.
And I knew very little geology, geochemistry, or molecular biology or biochemistry at the time, and I had to learn a lot. But Snowball Earth actually put it in that book, which I guess came out about 2000. But it's fascinating to see. For me, it was kind of very speculative, and now it seems to be, just part of what's accepted in general on the history of the Earth, and that growth of life always amazed me, because it seems to me, and maybe we're going to be useful for that when there's a global catastrophe, it seems to be good. It creates a lot of evolutionary niches for new life forms. So maybe humans will be useful for that.
Yeah. So one reason that was it wasn't just speculative; it was highly contentious. And one reason is, for 150 years, geology worked by assuming that there was nothing in geological history that didn't have a direct analog to what's happening now.
Oh, yes.
And then in the late 20th century, two big ideas sort of challenged that. And one was the bolide impact at the end of the Cretaceous that probably killed the dinosaurs, which is something that doesn't happen on a regular basis. And happily, the other was this Snowball Earth idea. And so in both cases, you still had to use the geological methods, assuming that there were various analogs with the present. Otherwise, you couldn't infer anything. But you were coming to a conclusion of a big catastrophe, which had been sort of a no-go region, because the early geologists would look at stuff and say, oh, this was Noah's flood, or this was some thing that we can't observe now. Yeah. And so it was hard for the field to accept that these things could actually happen. But it's an example of a sort of strategy for creativity, is to re-examine fundamental assumptions that everyone's making and see which ones might not work in all cases.
Well, and it's fascinating to see that, that's what's great about science. An idea which is incredibly contentious and deservedly contentious ends up promoting a lot of research, and and people can change their minds, and that's what's great. And eventually, the one hopes the correct idea wins out, and it generally does. The evidence is what drives it. But what Snowball Earth has a big impact on me, and this is why I want to go into your next area of work. I spent a lot of time, as a cosmologist and someone who's doing astrophysics, and I've written about thinking about life elsewhere and exoplanets, and have good colleagues who were among the first people to discover exoplanets, and I did a podcast with one of them recently. I take a lot. I want to see how contentious this statement will be for you. I take much of what I hear about astrobiology with a pound or maybe a ton of salt. It's an area where a lot of a lot is said and very little is known. We now know a lot more about the existence of exoplanets. But one of the things that interests me, because I know you've written a lot about habitable zones, and I think that would be the subject of a lecture of yours that we'll talk about in a little bit. But when I tell people is when people talk about habitable zones, that's thinking about a region around a star where there could be liquid water, which we tend to think of as a precursor, at least for life like we know. But then I think about it. Well, here we live in a habitable zone, and yet the Earth was frozen over in principle, at least twice. And therefore, one cannot assume when you hear someone say, oh, well, this is a region where there could be liquid water. A lot of those models don't even have continents. And as you point out, it was the existence of continents around the equator that probably had a huge impact on the cause of that freezing over. And therefore, there's just so much uncertainty that we should, while it's fascinating to discover there are planets that live in a zone where there could be liquid water, but one shouldn't jump to the conclusion that they're necessarily either habitable or indeed liquid water. So having thrown out those
I would say that that's not a contentious statement. I wouldn't consider that contentious at all.
Oh, okay.
I mean, I think this is like the hunting region. In fact, there's actually a professor from France, Francois Forget, he prefers to call it the hunting zone rather than habitable zone, which is sort of, he's implicitly trying to take this into account, that we should just assume that those planets are going to be habitable. There's all sorts of issues that, like, even if they have atmospheres, in a lot of cases, the ones orbiting smaller M stars, their atmospheres might have been blown off.
Yeah,
so they don't even have atmosphere. And actually, that's a funny case, because that lecture I gave that we're going to talk about later, I guess, was about these M star planets. And we haven't actually established that they have atmospheres. So for the past 10 years, me and a number of other research groups, we've been working on what the atmosphere of these planets would be like if they had an atmosphere. But it would be very funny if it turns out with the James Webb Space Telescope that they don't have atmospheres. That would be one of like those delightful little jokes that nature can play on you.
Yeah, and that's the right attitude. I'm glad to see, Dorian, you have that attitude, because you have to roll with the punches. And nature, nature decides what the world is really like, whether you like it or not. And well, that's talking about M stars most stars are smaller than the sun, and by a selection effect, most of the planets we see are closer to their stars than the Earth, because of the ways we use to detect them. So it's a lot easier to detect a planet that's closer, just because its orbit is faster, and you can therefore measure periodicity many times over and remove for systematic errors and things like that, and test. And so as I understand it, and again, correct me, I'm sure you'll correct me if I'm wrong, that most of the quote unquote habitable exoplanets, but namely live in habitable zones, are around smaller stars and therefore much closer to their stars. But by same token, those stars can have eruptions, and I mean, because they're much closer, those planets are much more susceptible to stellar variability or stellar processes, and it's therefore, we're here because we had 4 billion years or so of relatively quiescent activity, but in those planets, there may be huge effects that have blown off the atmosphere. So
there's 3 potential issues. One is that they're closer, so any stellar activity is going to be, more impact. The second is M stars actually have more stellar activity than G stars.
Yeah.
And then the third is, this is an interesting one because it relates to Lord Kelvin's estimate of the age of the Earth. Mm-hmm. The stars have a sequence. It's called like the Tauri, or I can't remember the name, but there's a sequence where I know the physics that when they're emitting because of their gravitational collapse, before they start emitting because of their nuclear burning. Mm-hmm. And that was all Lord Kelvin knew about for the sun in terms of where the energy could be coming from. And so we got an estimate for the age of the sun that was, tens of millions of years or 100 million years, and an estimate for the age of the Earth based on cooling with no convection that was the same. And he said, if the sun's the same as the Earth, then, I must be right. But of course, he was missing processes in both cases. But the point is, for the sun, that's maybe like 50 million years or 100 million years. I forget the exact time scale for that phase before you start the nuclear burning. But for M stars, it's actually a billion years or more. And during that period, the emission can be 1,000 times higher than it eventually is from the nuclear. And so that could also fry these planets.
Yeah, absolutely. I mean, I think it's Hitari. You can actually see these stars. I have images of them. Nascent stars are, and that's again surprising for some people. So let's reemphasize that, because you think nuclear, boy, powerful, but gravity during these periods of all stars' early formation, they can be thousands or up to 10 or 100,000 times brighter than the sun. That this period of gravitational collapse releases tremendous amounts of energy. I didn't know it was a billion years for them stars. That's fascinating.
By the way, I just want to say, I keep talking. Everyone wants to talk to me about all this silly business that I've gotten into, and it's really fun just talk about the things that I actually find interesting.
Well, good. Me too. And I think, I've dealt with a lot of silly business over the last many years, but the motivation is always the same, which is to get people to think about the world the way it really is. And that's why science is so much fun for me and you, I think. That's what attracts us. We don't mind being wrong, I hope. And the world is fascinating. And it's okay to recognize that, especially when it goes against your intuition. And that'll be relevant, I think, for some of the funny business so I think the motivation for both you and I in fighting some of the nonsense that's going on now is really the sense that, hey, let's use empirical data and let's try and understand things rather than making assumptions. And we should test our assumptions at the very least and be willing to question them, which is really what science is all about. So I'm glad you're having fun, because I think, well, as I say, this stuff is fun for me. And it's also, I think, fun for people. I mean, science is fascinating for people, and people don't often enough get the chance to really hear a serious discussion. They hear sound bites. And I think one of the reasons I do this is to provide that opportunity with the right people. And I'm glad to have you on for that. Okay. Well, before we get to the funny business, which I'm timing very carefully because I know our time is constrained, but we talked about Snowball Earth, but why don't you talk a little bit about exoplanets and habitable planets? Because obviously your own area of research, which was cloud feedback, is going to be important if there is an atmosphere in these objects, and the existence of continents, as well as the other fact, which I think is true for a lot of these M stars, certainly lower planets, is they may be tidally locked to the star, which means for the listeners, the same side is always facing towards the sun. So why don't you just do a riff?
Yeah. So the lowest tidal energy state is one orbital rotation, a rotation around its axis per orbital rotation. So you can get locked in other states, like Mercury does 3 axial rotations per orbital rotations. You can get in other integer ratios, but the lowest energy state is 1-to-1, and the moon is in a 1-to-1 state around the Earth, and that's why we always see the same side of the moon. It has a little bit of rocking back and forth, but basically it's in a 1-to-1 state. And so if you're closer, there's a very strong inverse scaling with the distance between the two objects. And so if your planet is much closer, the tidal time scale goes way down and you get tidally locked quicker. So we expect to find a lot of these planets orbiting M stars that could be habitable in a tidally locked configuration. And that's super, super exciting. That was what originally got me interested. So I read a book. I gave a talk in London. I was interviewing. It was when I was a postdoc for a faculty position. And then I flew back and I had this book that I bought by Jim Casting it was called How to Find a Habitable Planet.
Yeah.
And he had worked on the terrestrial planet finder mission with NASA. And when it got canceled, he wrote this book to try to get the public excited. And I read the whole book on the flight back, and it got me super excited, made me want to work on this topic. And so the immediate thing that I noticed was everyone was doing one-dimensional models, vertical, of whether a planet could be habitable. And so any horizontal heterogeneity due to things like, as you mentioned, continents, was gone. But then we were applying these to these tidally locked planets, which is like the maximum possible heterogeneity that you could imagine. The sun's all on one side and it's always night on the other side.
Exactly.
So that
always made me very skeptical.
And then the other interesting thing is we have all of this geophysical fluid dynamics that's been worked out for planets like Earth and what we see in the solar system, but we don't have any examples of that in the solar system. So it was a playground that was completely open, nobody else playing in it, to see what would happen if you tried to model this type of configuration. And so that's why I got interested in it.
Oh, no, I agree. I mean, I think I've heard it's institute that I once led had a prize lectureships, and someone was lecturing on habitable planets, and it was all one-dimensional models, and which means basically for listeners, that doesn't mean we think the planet is one-dimensional. It means basically everything is a function of only radius, and you don't assume anything across the surface, which is obviously the simplest thing to solve mathematically. And in a lot of astrophysics, we use that because it's the only thing we can do. Otherwise, it gets too complicated numerically. But obviously, for a lot of systems, it's not the right thing to do. And I've always, as I say, been skeptical. But unlike you, it was an area that I could then say, okay, well, I'll work on it. But you could, and you did, and have.
Well, so what's most interesting is the effect on clouds. And so just the bottom line of that talk I gave was we put the planet in tidally locked configuration, Earth-like planet, and it gets really hot at the substellar point, and then you get a lot of convection, and you get a lot of clouds, and those reflect a lot of solar radiation. And so what ends up happening is you can stick the planet a lot closer to the star than you thought you could, and it doesn't turn into Venus.
So effectively, what it means is that, you're distributing the heat more effectively. You have an additional cooling mechanism in the hot spot, and the heat gets distributed more.
Even more than distributed. So that's important too. You can distribute the heat to the night side and radiate it efficiently to space, but you just reflect the heat before it even gets into the planet. So it doesn't even get into the climate system.
Okay, well, I mean, it'll be interesting to see what happens, especially if they have an atmosphere.
Yeah, exactly.
and because once again, just to emphasize for people, the point is that if one a priori just counts planets and looks at ones where there may be liquid water, by far most stars are smaller than the sun, and therefore most of the planets that we're going to be thinking about for the next N years, scientists and maybe measuring and maybe discovering, will be planets close to the stars. The stars are smaller and the planets are closer, so we'll have to understand that science a little bit more. And of course, it's great excitement that the James Webb Space Telescope and maybe other things will at least give us empirical data to tell us more about those planets to compare with the kind of models that you've been building, Dorian. So it's going to be an exciting time.
So, and just two more things I want to mention. So
sure.
The PhD thesis of a student that I advised, Daniel Cole, in the same era when I was learning about tidally locked planets, what we did in that thesis was calculate the heat transport you would expect with an atmosphere, and what effect that would have on the thermal phase curve, or your measurement of the temperature on the day side versus the night side. So if there's more heat transport, the day side is closer in temperature to the night side. If there's no atmosphere, then there's a big contrast between the day side and the night side temperature. And that method has already actually been used once, and that's demonstrated that a close-in planet, closer than the habitable zone, orbiting an M star, didn't have an atmosphere because it had too high of a day side, night side heat contrast.
How was that measured?
You look at the thermal emission.
And we're able to do it.
It's primary and secondary conjunction, when you're looking at the day side versus looking at the night side. And so that method is going to be tried with the James Webb Space Telescope, which is supposed to be launched soon, on lots of planets orbiting M stars. And so that will be our indication of whether they have atmospheres. And then if they have atmospheres, then we can try more things to try to see what's in the atmosphere.
Yeah, it's great to have a sort of a first order test right away to know what to throw out.
And then the other thing is, you mentioned that eventually we want to look at planets like Earth orbiting stars like the sun. And the decadal survey of NASA that just came out made that a priority. And so they're going to try to build a large optical space telescope that could take actual pictures, resolved pictures of a planet like Earth. So not just looking at the signs from the combined star planet system. And the hope is that will be in space in the 40s or 50s. And so that's the kind of timescale we're talking about.
It'll be great. I hope to be around to watch it. I remember it's funny because talking to people who were thinking about doing that 30 years ago, trying to think about how it could be done and hoping it might be done by now. It reminds me of another field, dark matter, that I've worked on, where people were talking about, and I was developing ideas about how to detect it in the 1980s, and I thought, oh, by now it'll all be done. That's the problem of experimentalists. They actually have to do it, and instead of theorists. So it'll be exciting. It'll really be an interesting thing to do. And I suspect, again, if history is any guide, that we will be surprised. That I had one of our earliest podcasts with the head of the mission that went to Pluto, and every time we've looked at one of the planets, even in our solar system, we've been dramatically surprised about the dynamics. And so it'll be really an interesting time, because all of that new data will probably tell us that some of the ideas we have need to be radically changed, which is, if you're a scientist, incredibly exciting, I think.
Yeah, that's the best thing that can happen.
Yeah, exactly. The best that can happen, and we'll see. And yeah, it'll be interesting to see what comes of all of this, and it'll be amazing to see. There was a lot of interest when people saw a black hole, but I think getting actually imaging an Earth-like planet will be really
It'll be cool.
it could be a game changer for human civilization in some ways. One hopes, anyway, for these kind of moments, but we'll see. And let's hope we get there, because there are challenges to science in America, and you've been talking about one of them, and at least, and so I want to move on, because I guess I want to talk about the piece you wrote in Newsweek, you and Ivan, which came out, it was in 2020 or 2021?
This summer.
Yeah, that's right. This summer. So you and
August
Ivan
12th.
Marinovic wrote a piece, June or July, in Newsweek on diversity problems, which is an area I've been writing about and speaking about as well. And I want to ask, before I get to that, and it's an eloquent and beautiful piece. It's just succinct, and gets to the points. I just read it again, and I'd read it some time ago, and I was impressed. And I remember writing for Newsweek. I don't remember their editors doing much, so maybe they didn't do much to yours either. But what got you? Yeah, they just sort of published whatever I wrote, as I remember. But what? Well, let me read the beginning of this, and then I want to find out what led you to do this. It didn't come out of the blue. But the first paragraph's, I think, vitally important. It summarizes everything, so I'll read it. American universities are undergoing a profound transformation that threatens to derail their primary mission, the production and dissemination of knowledge. The new regime is titled Diversity, Equity, and Inclusion, or DEI, and is enforced by a large bureaucracy of administrators. Nearly every decision taken on campus, from admissions to faculty hiring to course content to teaching methods, is made through the lens of DEI. This regime was imposed from the top and has never been adequately debated. In the current climate, it cannot be openly debated. The emotions around DEI are so strong that self-censorship among dissenting faculty is nearly universal. That's just the introductory paragraph. So what was your experience that led to this piece?
Well, I guess, the long story is, I first heard about the sort of critical social justice framework when I was an undergrad at Harvard, around between 2000 and 2004, from non-scientists in the studies, the various studies departments.
Yeah, gender studies, other studies, yeah.
Yeah, particularly I had a girlfriend who was kind of in the gender studies kind of stuff. And at the time, I just thought, well, it's kind of like fun and silly, and they're doing like a fun critique of civilization, but no one's going to take this stuff seriously, because there's no evidence for most of these claims that are being made, and it's just sort of silly stuff, and it's okay, they can do their thing and we'll do our thing, and our thing to me is more serious, but they could do their thing, and I don't have any problem with that. And that's kind of how I thought about it until about 2015, in that kind of range. And slowly things just got more like, it was like, it it just started to come into my life as a scientist. And the beachhead was these diversity, equity, and inclusion programs. And so it was a way to bring this sort of orthodoxy that doesn't observe the Mertonian scientific principles into science. At first, my response was basically, I'm just going to keep my head down and stay out of trouble.
Which is what I think, by the way, to first approximation, that's what 95% of faculty members do. But in all cases, when anything is happening at the university.
Well, especially in science, I mean, like, how do you get to be a science tenured faculty at one of these universities? You're the kind of person who just puts his or her head down and does the work and doesn't worry about all this other junk.
Yeah.
And so that's what I did. But I sort of started self-censoring. I was nervous because there started to be all these landmines that you could step on in the department, in my department, where, like, you say the wrong thing and people are going to yell at you or report you to the department chair for saying the wrong thing and all this kind of stuff.
Let me interrupt you, because it just, when you talk about this, and this is probably relevant for you and for understanding many faculty, you said it changed around 2015. Is that when you got tenure?
I got tenure, I think, a little before that.
Yeah, I mean, I noticed you became an associate professor around 2015, and I thought maybe that's when...
maybe it was then. Yeah.
Yeah.
But that wasn't the reason, but maybe.
Yeah. No, I mean, for many junior faculty, they're especially worried about speaking out. So I didn't know if maybe the getting tenure, which, in tenure is an interesting thing. For before you have it, it means a lot, and after you have it, you can kind of forget about it. But it may have given you the freedom intellectually to begin to worry about things that you might not have worried about otherwise, or am I jumping to conclusions?
It's possible. But if you talk to the social scientists, which I have after this, there was a transition in the way this stuff was being talked about in society that happened in that range. Just to give you an example, I remember, it was a surprise when Donald Trump was elected president. Yeah, and I remember one of the explanations people gave was, people are afraid to tell pollsters who they actually want to vote for. And at the time I was like, what? People in the United States of America are afraid to say? That's complete bogus. But now I can see that had already started to get out there in society, that, people were afraid to say what they actually thought.
Yeah, no, and as someone, at an upper level of the university, seeing faculty generally being afraid was a fascinating change. And you're right, it's a sea change. In a longer term, I taught at Yale back in the 80s, and that was when deconstructionism and postmodernism was a centerpiece of the literature, the English departments, and we on Science Hill just sort of laughed at it and said, well, it's not, it's just, it's okay, it's all right. But it changed changed dramatically in two ways. One, from laughter to concern, and another from, it's just affecting those touchy-feely departments and never will affect science, to suddenly finding that it impacts on science as well. So, yeah,
I think the unfortunate realization is that the humanities really are at the center of universities. And when something goes wrong in the humanities and they lose faith in themselves and get off on postmodern tangents, it's going to come around to get everybody in the university.
You're right. And they are. Yeah, good point.
So then, I think at first I was content to just kind of like avoid people that I knew would cause trouble about these issues and just keep my mouth shut. But it became increasingly hard to function. And one issue that I found really important is the type of work that I do is very creative. It's not the sort of thing where it doesn't work well if you're in a stifled situation where you have to watch everything you say. It's really hard to go into a department, have lunch with people, and it's like you're in the Soviet Union, and then retreat to your office and you're supposed to be in this like creative space. It's just, it's hard to do that. And so
it's true for all. I mean, that's another thing. I mean, it's you're right for the work you do, but people don't think of science as a creative activity, but like all the other aspects, it is a creative activity, and without being able to throw out any idea, no matter how crazy, to bounce off others, then you have a problem.
You've got a real problem. So that started to bother me. But the real switching point where I felt I had a moral duty to speak out on these issues occurred starting around 2019, 2020. Actually, the first was 2017, but it started to ramp up. And I was on all these committees for, selecting people, and there was open discrimination against certain groups. And so the most important groups that were being discriminated against are Asians, both Asian Americans and people from the continent of Asia, and men. So for things like hiring, who gets to go to conferences, who gets chosen to give lectures at conferences, people would just say like, well, like for admissions, we don't need any more Chinese students, we need more diversity, like a very open discrimination, not evaluating people as individuals. One thing that really bothered me was I was on a faculty hiring committee, and we were told that the dean would only consider a person, he would not, if we nominated for the faculty position a white or Asian male, that he would throw it out. And this was done in a kind of backhanded way. It was passed to us. It wasn't given to us in writing, but we were told through multiple channels that that's what we should understand the context of this search. And that just really wore on me, and it felt immoral because we were writing on our job ad, we're not going to discriminate on the basis of X, Y, Z, but we were actually in private discriminating. And this was happening pervasively in every committee that I went on to do this. And it always came up in the context of this thing called DEI. And I started to realize that DEI doesn't mean what I thought it did. So when I started, I thought it meant, we value diversity, and our goal is to have, the best science possible. And that means we have to examine our biases and make sure we're not biased against everyone. But, if it turns out that 80% of our theoretical physicists are like Jews of Eastern European heritage, we're okay with that. It's just as long as we're not biased against anyone.
Yeah.
But it turned out that that's not what it meant. It meant something much more like we're trying to get our numbers into a range that's acceptable in some way. Often that's some sort of comparison with a population. And if we don't have those numbers, we're just going to make it happen. And it's a more important goal than doing, advancing scientific knowledge. And that, to me, that was crossing a red line for a number of reasons. The first is just, I actually care about the goal of the university. I think it's important, and I'm not going to give it up and substitute a different goal. And the second reason is I think I believe in equal treatment as a moral and legal principle, and to see it violated so openly, it's a really scary situation, because when that's happened in the past, it's disastrous things have happened to countries. And so that's why I decided I had to speak out about it.
Well, and you summarized, the argument here follows what you just said. The second paragraph really talks about, hey, diversity, equity, and inclusion they sound good, but they don't, I really thought that they don't really mean fair and equal treatment. And this idea, the underlying premise of DEI, as you write, is that any statistical difference between group representation on campus and a national average reflects systemic injustice and discrimination by the university, an assumption for which there is no, as far as I know, no empirical evidence. And moreover, an assumption which I've learned, as you know, because I think we may have communicated, I in response to a piece I wrote recently, some lawyers wrote to me about a famous university case, Supreme Court decision on affirmative action, where, and this is why I actually am wondering why no one's carried this out, that according to this Department of Justice memo, which I then read, it specifically says that it's all right to consider, in certain cases, racial issues, but to demand that representation reflect, demographics at a national level is unconstitutional if the pool, for example, if you're looking for electrical engineers and the pool of black PhD engineers is not the same as the 12% of the American public, but maybe 3%, then when you're trying to get 12% percentages in your department, it's actually unconstitutional according to that kind of argument. That it's not only unwarranted from a point of view of assuming racism and systemic racism, but it's actually also legally inappropriate.
Well, so it's a little complicated. So my understanding of how that works, neither of us are lawyers, so we should
happily, otherwise we wouldn't be having this conversation.
But there's there's a ruling in 1978 called Bakke.
Yeah, that's the decision.
This was a med student who sued the University of California because he was being discriminated against. And it was decided in a really weird way. What they basically said was, we want to figure out a way that Bakke can win and get admitted, but we don't want to cause too much trouble for affirmative action programs. And so what the decision ended up saying was, you can have an affirmative action program as in undergraduate and graduate education, as long as the point of it is to improve diversity. And that's why this word diversity has become so important in the past 40 years. As long as the point of it is to improve diversity, not to as a sort of retribution for past actions.
Or to discriminate against various groups.
Yeah. But then the rulings by the Supreme Court related to employment have always maintained that you can't take into account diversity. And so that's one key distinction that I've learned about since I've studied these issues, is that for the sort of thing that I observed in these hiring committees and stuff, that's really getting into dangerous territory legally.
That is illegal, at least as far as I can see. And I've been part of them for 40 years. What's being done explicitly is directly in opposition to at least what the judgment of in that case argues should be allowed. But look, we're not lawyers, and I think.
Let me just say one more thing about that.
Okay.
So what I've learned now, what I would have done when I was in that instance, when I was just like feeling manipulated and didn't know what to do, what I would do now, and what I recommend anyone who's listening to this to do, is say, I am not going to base this search on a verbal instruction. I want to see that instruction in writing, exactly what you want to do. So force them to put in writing, and then once they put it in writing, say, I'm uncomfortable with this. I want it approved by our general counsel with a report in writing. And so that's what I would do moving forward.
That's a wonderful.
You find yourself in a situation like that.
Yeah, I mean, if you have the guts, because the universities can become very vindictive when you do that, and it's remarkable to see that. But look, I think that's you're getting. I want to, before we get to the end, I want to talk about what we can do, but I don't want to harp on this so much on the legal issue as the question, the scientific. What offended me as much as anything else was this scientific assumption of taking something on faith without ever testing it, which goes against the antithesis of everything that I think should be the key for academics in general and scientists in particular. And the notion that any difference between representations must reflect systemic injustice and discrimination. When I was a faculty member for 40 years, and I have to say, there are individuals who are idiots, but systemic discrimination never, or systemic racism. That claim just goes against everything I can see. Universities, as far as I can see, for better or worse, maybe not any longer, but have been the most enlightened places you can find in American society. And to argue that these things reflect anything other than social situations. I mean, I was chair of a department at Cleveland, and I used to go in the public schools in Cleveland and see what the disadvantages that you had, and there's where you really had to put energy in to try and, you can't solve a problem when kids don't have textbooks in schools or adequate teaching, and so I want to just throw out to you that concern that somehow this reflects something for which, as far as I know, no one has provided any real evidence.
Well, it's not only that, but we have strong evidence to the contrary. And
exactly.
So, for example, if you send faculty applications without the sex listed, women are favored by a factor of 2 to 1. And there's a PNAS study of that. And that's true for all, in all of these situations. There's actually demonstrative preference for the underrepresented groups. The other issue is, I think it's important to note that it's hard to do science. It's hard to be in the scientific mind frame. We have to have peer reviews to remind us, to not make all of our stupid assumptions. And so just the fact that we're scientists doesn't mean that we're going to be able to do science all the time, especially when it gets into these emotive issues.
Yes.
And you can see, I've experienced it so many times, colleagues who I totally respect as scientists just saying total phooey because they read it in their favorite, blog or their favorite journal, and they don't question it at all. And it's funny because we know when our articles are covered in the popular press. I mean, the journalists do the best they can, but they're just not technically trained, and everything gets all warped and messed up. And so it's obvious that must be happening when they're reporting on these other issues. And then you add to that they often have a political stance that they're trying to sort of promote. And so, yeah, it's just crazy. It's crazy to watch rational scientists get so confused.
And that's why science works. I mean, the point is that scientists aren't, science, I once said if I was actually on the side of a debate at Oxford University recently where I said everyone's religious, in the sense that if people weren't, then we wouldn't need science, in a sense that science is a set of tools that helps us overcome the individual biases that we know scientists have. But together, socially and as a group, we can overcome those biases. We can question them, test them, and combat them. And you're absolutely right that I think that's what we've already seen happen. We already see the process, the way my experience, and I've got to ask yours. As a particle physicist, which is where I come from, I see Large Hadron Collider at CERN. I go there, 5,000 physicists from 100 different countries, from 20 different religious groups, from every different racial and gender group you can imagine, and no one's asking. They're just, what the people are concerned about is, will this device work when it's fit in a mammoth detector? And it by nature, science is based on just looking for things that work and not asking who created them or where they come from.
Well, I think the idea you mentioned before, these ideas of systemic systems of oppression.
Yeah.
And I think where those come from is, when you try to actually demonstrate racism or sexism in these processes, the evidence you can find for it are few and far between, and often goes in the other direction. And so then if you believe that the explanation must be racism and sexism, you have to fall back on a nebulous concept of a systemic thing that's difficult to even define, let alone measure. And so that's, I think, what's driving those concepts.
And that's a religious view, I would say, because I kind of think of religion as something where you know the answer in advance, and you interpret everything that you see to validate your answer. And this is kind of secular religious thinking, where we know the answer is systemic racism, and therefore we'll look for anything that can validate that.
Yeah, I mean, there's a variety of ways to approach religion, some of which are more in that category, and some of them are more, rationalistic.
Of course, yeah. And I'm just looking, to make it clear, I'm glad you're saying that. I mean, I'm looking at that aspect of religion. You're right. And in fact, I often say the problem with this secular religion is that, at least in some things like Christianity, there's such a thing as not just atonement, but for what's the word where you forgiveness, that's missing in a lot of this. But I wish we had more time, but I want to get near the end. And your comments are fantastic, and I really appreciate them. In this article, I think no, not in this article. In your webpage at the university.
Yeah.
You say, I practice fair admissions. I select students and postdocs on the basis of scientific ability and promise, and I do not discriminate against any applicant on the basis of anything else. I encourage freedom of expression and the creative exploration of ideas in my group, which is a profoundly important statement, and I think is kind of the basis of what you now would call your alternative framework called merit, fairness, and equality. So I want to give you a chance to spend a minute or two at least talking about that.
Well, so the concept there, so that's a statement that I came up with, a year or so ago, because people were putting all these statements on their website about, how they agreed with DEI stuff. And so I wanted to say what I think. But the merit, fairness, and equality, the idea there was not to just knock down diversity, equity, and inclusion, but to come up with a positive alternative. And the goal there was what I thought originally DEI was about, was to, we're going to try to make merit evaluations that are fair and that are where everyone is given an equal chance. And so the equal there means an equal chance, not equal outcomes.
Yeah.
And so we haven't, Yvonne and I didn't define that in depth. We just sort of put it out as an idea, and other people have run with it in different directions. And that's the hope, is that people, we'll give people an alternative. And I mean, the dream was, the unfortunate thing about the way academic politics work is you've got these administrators that once they get in there, they're not going away. And so I was just hoping, like, maybe we could just get those administrators to, instead of being DI administrators, they could be merit, fairness, and equality administrators. And, they could all get paid, and, the tuitions can keep going up, and they can keep hiring more minions to help them, little administrators and sub administrators, and then deans and whatever. But they'll at least be doing something that's advancing the goal of the university,
instead of getting in the way of it, instead of interfering with it. Yeah, no, look, I think it's a noble goal. I'm beginning to think that that's an optimistic one, and that we have to look at dismantling what exists already. But I want to end with, look, I mean, I wish I could say that I would have contacted you to have the conversation if I and then I would have known you more for the work you've done on fascinating work, which I enjoy talking about. But what I particularly am, I don't know the word is happy, but I was kind of happy. I keep looking for triggers that may finally influence not just the public, but academics about how bad the situation's become. Because when I write about this, I always say, oh, it's not really that bad, or, it can't be that bad. And so you became a flashpoint for a poster child, if you're forgiven the expression, with what happens. You were going to be lecturing on what you and I were talking about, the fascinating science of life and the possibility of habitable planets, the stuff that people are really excited about, high school kids and everything else, the kind of things that would really encourage kids to go into science. You were going to give a talk at MIT on that. And because of the opinion piece that you wrote, MIT canceled that lecture. So maybe, and the argument they gave was, hey, we're trying. I read the argument after the fact, as far as I can know. Hey, this is really meant to encourage our students, to bring people into science. And you're a divisive figure now, and it won't bring people into science. So maybe you could just spend a minute or two commenting on that.
So I mean, what happened is the heckler's veto, pure and simple. So a small group of people organized on Twitter, and they said, essentially, some in so many terms, some not in so many terms, we're going to cause trouble if this guy gets to come give the lecture. Like, we might disrupt the lecture, we might yell, we might protest. We're going to go on Twitter and say that MIT is a racist, sexist, et cetera, all these words that everyone's scared of now. And so they just said, well, we don't want to have that controversy, so we're just going to avoid it. But the funny thing is, they made it seem as if I had caused a controversy, whereas in fact, I had nothing to do with the controversy. I simply had stated my opinions on a totally separate issue, and then this group had caused the controversy. But it's incredibly damaging for science if this was a large honor in my field, if honors and recognition are given out by who's loudest on Twitter rather than, who's done the scientific work that merits them. And everyone in the public should be aware that the things that I've been advocating are supported by 3/4 of the public, including the majority of every race and both political parties. And so we're now at the point where your scientific career can be challenged and derailed just for saying things that everybody in your personal life agrees with, that only someone who's an extremist would not agree with. That's now gets you so that you can't go around and give lectures and stuff. And
it's not that they determine who gets the prizes, but they determine who don't get these things. And I've seen it at a personal level. And it's more important than just that, Dorian. I think it's not just that it's a shame when people who say something that most sensible people agree with, that they can be canceled but we have to have a society where people who say things that people disagree with can speak out.
I agree 100%. Yeah. So I'm just saying that demonstrates how dire it is. It's not even someone stating something that's, particularly contentious.
Exactly.
And the other thing I would say to the public and to anyone listening, there's some guy in a lab right now, this is hypothetical, who's finding the cure for cancer. Okay. Are you willing to give up the cure for cancer because he voted for Trump?
Exactly.
I mean, where are you going to take this? I mean, who gives a crap what someone's political opinions are or moral opinions if they're doing good science?
Or more likely, forget voting for Trump, more likely, are you going to stop them from doing the research? Because they say, I don't really care about social issues. I'm not trying to save the world. I just want to do my work. Leave me alone. And which
exactly.
Which is probably more frequent.
Yeah, silence is violence in this ideology. And so it's just as bad to say, I don't want to deal with that as to say the hated bad opinion.
Well, we're out of time because I know you're constrained by something. I was hoping the last thing I want to do is say, what can we do next? You've already indicated something useful, which was what you can do if you're a faculty member, which is really important to get things in writing and be willing. Although, again, I counsel junior faculty a lot, and I don't want any junior faculty to put themselves in danger. They shouldn't do anything they should feel uncomfortable with. But if they believe in this, there's certain steps they can work on. But mostly, I want good young faculty who are doing science to be able to do science. And I don't want to put themselves on the chopping block because of an issue that I may think is important. But any other last words?
Recommendations? Yeah.
Sure.
So if you're an alumnus or an alumna, tell your institution that you're not going to donate money anymore until they adopt the Chicago principles, which are free speech, and the Calvin principles, which say that the university can't take political positions, and actually enforce them, not just adopt them, but actually enforce them. You can also make a group of alumni. And so MIT alumni did this after my affair there, and have been saying, like, look, we want our institution to be what it used to be, not the Critical Social Justice Institute of Technology. And so that's something you can do. And if you're a member of the public, you can talk to your legislatures and say, look, we're funding these institutions, even the private ones, because they're getting all of these grants. That, the reason we have all of these diversicrats is because we've got so much, we can jack up our tuition and hire hundreds and hundreds of administrators. And that's all because we get all these federal grants for tuition. And so say, look, we want to attach conditions on those federal grants that political neutrality and academic freedom have to be observed. And there needs to be a certification that's being done internally and externally that ensures that's happening. Same thing for federal grants for science. Say, if you want to get this, you cannot compel speech. You can't force ideology. You have to select people based only on merit, and you have to allow your employees to say what they think. And so those are the sorts of things that could start to have an impact.
Absolutely. And it's worth pointing out that right now the opposite is happening in some sense. There are federal granting agencies that are saying you can't get a grant unless you have 50% X. And that's just horrendous. And so it's not just a matter of making it better. It's a matter of counteracting the negative and then working towards the positive.
And one more thing I would mention is that human beings have a problem of tribalism. So, we can just approach that from an empirical standpoint, that's an issue with human beings. And all of these efforts are projecting onto that tribal eigenvector in a bad, dangerous way. And so we all have something at stake here to slow that down.
We do, although if you're a member of the medical community, as I've written now, you're not allowed to, the Journal of Medicine, you're not allowed to use the word tribalism, because it's offensive.
Oh, great. Okay, yeah.
They changed a medical article where they took out all that.
What do you use now? What do you use?
I'll send you the link. It was just ridiculous. It was absolutely ridiculous. They retracted the article that an author was writing that there shouldn't be tribalism in medicine. And the journal said that's offensive. And they retracted the article. The editors rewrote it, getting rid of it, even though tribalism was defined in the article. And got rid. That's the kind of nonsense we're dealing with.
So let me give you a point of warning. Bless the philosophers, but they're not arguing about the big questions anymore. Instead of arguing about the meaning of life, they are now arguing about the definition of definition. Yeah. And I think that's what happens to a field if you get obsessed with all of these minutiae and you forget about the actual point of why you're doing the research. And so that's the danger. We don't want to go there.
Well, yeah, we don't. And look, it's been a pleasure. I appreciate you taking the time. I really enjoyed it. I hope you enjoyed it. And I've, as someone who's also had actually a public lecture once canceled at MIT for something I said, I'm really
we're in the club together.
Yeah. But thanks again, and I look for and it was fun talking about science, and I really appreciate it. So thanks for coming on.
Yeah, it was really fun.
I hope you enjoyed today's conversation. This podcast is produced by the Origins Project Foundation, a non-profit organization whose goal is to enrich your perspective of your place in the cosmos by providing access to the people who are driving the future of society in the 21st century and to the ideas that are changing our understanding of ourselves and our world. To learn more, please visit originsprojectfoundation.org.